Okay, moving along, our next speaker is a highly recognized and well-regarded member of both the academic research and practical application fields of security, cryptography, and MPC in particular. Dr. Nigel Smart earned his PhD from the University of Kent at Canterbury in 1992. He worked for a number of years at Hewlett-Packard, and then he transitioned into research and teaching when he joined the University of Bristol in 2008. In 2018, he transitioned to the COSIC group at KU Leuven, which is regarded as one of the top 50 research and teaching universities in the world. Nigel's held a Royal Society Wolfson Merit Award and 2 ERC Advanced grants. He was vice president of the International Association of Cryptologic Research in 2014 to 16, and in 2016, he was named a fellow of that organization. In his spare time, he was a founder of the startup Indentum, which was brought by Trend Micro in 2008. In 2013, he co-founded Unbound Security, a company deploying products based on multi-party computation. And he's also the co-founder of the Real World Cryptography Conference Series. Please join me in welcoming Dr. Nigel Smart. Nigel?
So, welcome. We're going to overview MPC versus different forms of privacy enhancing technologies, or PETs as they're known. And MPC is a type of privacy enhancing technology called because it allows computing on encrypted data. So it's a kind of co-ed technology. So privacy enhancing technologies can be divided into these different camps. There's statistical techniques, which involve differential privacy with federated machine learning. We have more cryptographic techniques on the left-hand side of this picture, which is multi-party computation for the Homomorphic Encryption, zero-knowledge proofs. And then at the bottom, we have like hardware-based techniques. And these are they have different pros and cons, and you can do different things. So let's kind of look. So it's really easy. It's nicer to examine these technologies when you actually have something concrete to think about. So let's think about something really simple. So what we're going to do is we've got 3 entities, A, B, and C. They've each got data on 100 people, age, height, weight, whatever. And they want to compute some joint function on the data such that no private information leaks. So the individuals that party A has data on, when we do the computation, we don't want this to leak to party B or party C. And in all cases, we're just going to compute the average, because the average of something, the average age, the average height, the average weight, or whatever. Because this is nice and easy to do. And then we're going to kind of see how it generalizes to other problems. We're kind of going to focus on machine learning style problems because that's what kind of people want to do. But you can imagine you could compute averages, you could compute standard deviations, you could do pie charts, histograms of the data, generalized linear models, deep neural networks, whatever. Everything's just computing a function. So, but here we're just going to focus on averages. Okay. So what's method 1? So method 1 is to do it in the clear. And what you do is just give your data to a third party. So imagine you've got some cloud service provider here that you're going to send the data to. Clearly there's no security. You've given all the data to them. You could also kind of send all the data to party B, and party B could do it. But all the data leaks. So we have no privacy. So the variant on that is what's called a trusted execution environment. So when we send the data to the cloud provider here, it goes into some special form of hardware. And this special form of hardware, all the data outside the hardware is encrypted. And then when it goes into the hardware, it's decrypted and algorithms can run on it. That's what's called a trusted execution environment. In the industry, this is often called confidential computing, as opposed to secure computing or something else. This is confidential computing. And the entire security, the reason the cloud provider does not get access to the data, rests entirely on the security of the hardware. Now, there are 2 complexities here. The first complexity is that usually confidential computing is used when one entity wants to send data to the cloud and compute on it. And so therefore, a lot of the provisioning is designed for that situation. In this situation, we actually want to share data. And in some sense, it's not that well designed for that. So provisioning becomes more complex. The second and bigger problem is that within this trusted execution environment, it's actually running a modern processor. So in some sense, it has all the pipelines. It has deep out-of-order execution, deep pipelines, superscalar execution, etc., branch prediction. And what all of those things do is they create side channels. And side channels are where data leaks because of what the device is doing. It could leak from power consumption. It could leak from the electromagnetic radiation being emanated by the chip. It can leak from timing information. And so you are susceptible to side channel attacks if you use a trusted execution environment. Now, in the real world, there is no evidence this has actually happened on real devices deployed in the real world. But there's plenty of academic evidence that this is possible, and it seems almost impossible for a trusted execution environment to completely protect against side channel attacks just by the very nature of the beast. So you've got to ask yourself the question, if you don't trust the cloud environment with the data in the first place, because that would be method one, why do you trust them not to run a side channel attack? Okay, so you've got this kind of issue that's kind of there in the background. So that leads us to our method three. Now, method three is federated computation, which is a term I've coined. It's usually used in the words of federated machine learning, but we're going to do it for arbitrary computation, and it can often be applied to various computations. So let's see what this means in our situation of computing an average. So what we do is each party locally computes the function themselves. So for example, here we have that this party computes the average x, this party computes the average y, and this party computes the average z of their data, of their 100 people. And then we just combine them together and divide by 3. Okay, so we compute the average that way. Now, the local average definitely leaks. We definitely leak the average of party A's results. Now, maybe this is okay, maybe this is not okay. But certainly, information leaks. And you have to be really, really careful here because you have to consider the bigger picture. It's not just this query. You have to look at how much information leaks over all queries. So a classic example is if you suppose you want to take two averages. You take an average of 51 people, say all the people who are height graded, age graded in the 10 or something, and then you take a subgroup of 50 people. And so what happens is by taking an average of 51 people and an average of 50 people, you actually reveal the information of that extra, the 51st person, yeah? So what happens is that taking averages still leak information. So one way what we could do to repair this problem is use what's called differential privacy. So differential privacy, what it does is it adds a bit of noise onto the average of party A, adds a little bit of noise onto the average of party B, adds a little bit of noise onto the average of party C, and then combines them. And the idea is that you just want to add just enough noise such that you hide individual data, but not too much noise is added so that you actually still get the value of the result out. So you've got this kind of problem. You've got this Goldilocks dilemma. Too little and privacy is compromised. Too much and utility is compromised. Now we could do this for much more complicated tasks, which originally came in, like I said, federated machine learning is where this idea comes from. But it's really hard to see how you would apply this in general in federated machine learning. Unlike the average example, it's sometimes quite hard to apply the differential privacy technique because you don't really understand for example, you apply this to a neural network. You don't really understand how much noise you need to add to the neural network to hide data. After all, machine learning models are rarely explainable, and one needs, in some sense, to argue that some partially inexplainable model does not reveal private information. So there's no real formal security guarantees that federated machine learning does not reveal private information. There are maybe statistical arguments, but we've seen even with averages, simple "it's hidden in the statistics" arguments do not stand up to closer analysis once you allow more complex queries. Okay, now we come on to our fourth example, which is homomorphic computation. So imagine we've got some sort of additively homomorphic encryption function here, which is an encryption function which allows us to take two ciphertexts, an encryption of X and encryption of Y, and you could just combine them to obtain the encryption of X plus Y in a completely public manner. So here's how you would compute the average. So you'd have the person who wants to obtain the result is this guy. He produces a public key secret key and gives the public keys to the three parties who have got the data. They then encrypt their data, or their averages if you want, and pass them to a third party which does the computation, and then the third party sends the ciphertext back, who can now decrypt and divide by 3. Okay, so this is how we would compute the average in this situation, and this is it's secure. Okay, the key point in homomorphic encryption, though, is that the decryptor, this person on the previous thing, this guy at the top, has to be different from the person doing the computation, the guy at the bottom. They can't be the same. Because if they were the same, the person doing the computation would have the decryption key, they could just decrypt the data, and we're back to method 1, which isn't secure. Now, there are very fast linearly homomorphic encryption schemes which allow us to compute averages like that. If we want to compute so-called nonlinear functions, anything more complex, such as a standard deviation is complex in this environment, then you need what's called a fully homomorphic encryption scheme. And so a fully homomorphic encryption scheme is one that allows both additions and multiplications. Now, with current technology, we can use homomorphic encryptions to encrypt functions which are what's called low multiplicative depth. Basically, when you write out the function as a polynomial, this means it has effectively low degree. It's kind of intuitively what you could think about. So it turns out that it's quite nice is that most existing simplistic machine learning models have relatively low depth in nature. Think of a decision tree or a support vector machine when applied to data. The problem is something like an activation function used in the neural network is highly non-linear, but you can use special techniques. So you could conceivably, and there are companies doing this, evaluate private machine learning algorithms on private data. Depends on the precise algorithm, depends on how much data, but that's plausible application of homomorphic encryption. One of the problems, though, is training machine learning algorithms using homomorphic encryption is beyond what we could currently do, because training machine learning algorithms is at the moment a very complex task. You're training machine learning, like a deep neural network, you use huge amounts of computing, so it's very hard to use that with homomorphic encryption. So this comes on to what we're here to talk about, MPC. So what is MPC? Well, MPC effectively achieves the same as homomorphic encryption, but instead of requiring a single computing party, we use multiple computing parties, who could be, in fact, the data owner. And the security comes from the use of multiple parties. And the idea is that you can't trust one of the parties or two of the parties to behave honestly. And if you are one of the parties, you trust yourself to behave honestly. So your security is guaranteed just by the fact that you've got multiple parties there. And the idea is that we do it by what's called secret sharing. So the most trivial form of secret sharing, if we had our 3 parties doing the average, is that we split every single data out by x equals x1 plus x2 plus x3, and then we give xi to player pi. It then turns out computing linear functions is trivial, just like computing the average, but nonlinear functions requires interaction between the parties. So here's an example. We've got some data that's owned by player 1 here. He takes this data, he splits it up into x1, x2, x3. He keeps on hold of x1 himself, gives x2 over here and x3 over here. And even if these 2 parties gang up together, they can't find out x because they don't know the secret x1. So that's kind of why security happens. And then we use interaction to compute the desired function. So that's what MPC does in a nutshell. And we can recover the result. We can recover the result publicly, or we could want, if P1 want P1 to recover a result, we can do that. Okay, so whilst FHE requires a large amount of computation to compute nonlinear function, MPC requires a large amounts of communication, so we kind of trade one for the other. However, as technology currently stands, we can always compute MPC, always faster than FHE, by a few orders of magnitude, not by a small amount, but 2 or 3 orders of magnitude. So we can compute relatively complex functions relatively fast. The problem is you need multiple parties, which needs to fit into the business model. And they have to be genuinely distinct. You can't just say, okay, we're going to compute we're not going to have just 2 computers in the cloud, in the Amazon cloud, because effectively then you're just trusting Amazon. You're back to method 1 if you do it like that. And the other problem is the parties doing this have to be tech savvy enough to adopt the solution, which is complex because it's a complex technology. So it's currently defined in a number of situations, usually for bespoke solutions for a specific problem or for a highly repeatable problem space. So there's still issues, okay? Even if you do secure computation, you still may require differential privacy to protect the results. Just like when we computed the average, if we compute the average of 300 people, if we do multiple queries like that, we can still leak information. So you still might need to add differential privacy. And the differential privacy you might need to add on in a secure manner. In other words, within the MPC itself. So, because if you don't, you just peel it off. You could imagine that you could combine MPC and FHE with federated learning. You could use MPC and FHE to combine models in a federated learning example. But then you've got some attacks, how do you know if this party's using the same data, has not tweaked the model, or all sorts of other things. So there are kind of issues that you have to do, but you can combine these techniques together. But there's other differences between MPC and FHE. It's not that just one uses huge computation and one uses huge communication. In FHE, on its own, you trust the person computing the function to do the correct thing. What if they compute the wrong function? What if they, instead of computing the average, actually leak the age of the person, the target that they're trying to find the age of? So you have to trust the computing party in FHE to do what he wants. Whereas in MPC, for most deployed protocols, that comes for free. These active attacks become impossible to mount. Active attacks are not just about getting the wrong result. They can lead to a privacy breach. If you compute the wrong function, the function could be adversarially chosen and it could just leak the wrong the data that you're trying to protect. To secure FHE against active attacks, you need another form of PET technology that we see a lot of at the moment, which is what I call method 6, which is verifiable computing or zero knowledge proofs. Now, VC and ZKPs are roughly the same thing. Then they basically solve the problem is if you ask someone to compute something on your behalf, how do you know you've done it correctly? Which is our problem with FHE, yeah? So let's assume the computing party has some data ABC that's committed to in some way, and we ask it to compute a function. So what we do is that it computes a function along with a proof that it's computed the correct function, the function we asked it to compute. Now, if there is no private information, this is what's called verifiable computation. But if there is private information, which is what we got in this case, ABC, then this is what's called a zero knowledge proof. And the key point is that verifying the proof should be faster than generating it, because otherwise, why would you make someone else do the computation for you? Now, ZKPs are used a lot in blockchain applications today. They really are really amazing, and you can do really, really complex things with them. We at KU Leuven, we're working on a DARPA project where we're verifying bugs in existing code without revealing the bug. So these are really complex functions you're computing. The generating the proof is the hard bit, which is bit, but usually verifying the proof can be done in matters of milliseconds. But yeah, there are some issues with VCs and ZKPs. So in summary, PET technologies come in many flavors. Each has advantages and disadvantages. Major issues not only match the PET to the security requirement, but also to the business requirement. In that business requirement with the FHE, we needed the person doing the computing and the person doing the decrypting to be different parties. So they have to be separate entities, different businesses. And the issue is not just computing something without revealing the data. You need to compute the correct function, because even if you compute the wrong ones securely, you could still lead to a data breach. So, is this something for now, or is this something for the future? Okay. So, finally, what we can see is in the last 10 years, we've had massive investment in MPC and FHE. There's been DARPA programs which invested around $200 million. There's been EU-funded programs which have been conducted since the 2000s. So there's huge amounts of very, very deep technology been developed in industry and in academia. Venture capitalists have poured vast sums of money into this in the last 5 years. One report I read recently said that around $850 million have been invested in PET technology so far by venture capitalists. And Luna Ventures, which is a VC firm based out of Berlin, estimates the PET market was going to be around $1 trillion by 2040. And there's many companies working in the space. If we look at TE companies, confidential computing, they're usually the big players, ARM, Intel, etc. FHE companies, there's a bunch of startups. I mentioned a few there. There's others. There's an organization, homomorphicencryption.org, you can look at. And you're here because you're interested in MPC. And MPC, there's a huge number of companies. And there's this amazing organization like MPC Alliance, which of course you all know of, which is using this. So it's really here. It's here now. It's being deployed now. It's being deployed by big companies. It's being deployed by small companies. We've got loads of people producing products. It's here. So you've got to take aware of it, to take account of it. So I hope it's been useful in comparing the different technologies for you.
Thank you, Nigel. I'm always impressed at how you can take such complex topics and boil them down to a level that makes them so much easier to understand. Unbound Security was one of the co-founding members of the MPC Alliance, and we always appreciate your efforts and the Unbound Security team as well.